Hello fellow problem solvers. Today we're going to be doing a simple introduction to polynomials, and we're going to start off with this problem. Let p of x and q of x be polynomials with real coefficients. If p of x is equal to q of x for infinitely many x, prove that p of x is equal to q of x for all x. Okay, now how are we ever going to do this? Right, so what does it mean that p of x is equal to q of x? Well, it means if you graph these polynomials, right? They say p of x is this, and say that q of x behaves differently like this. This thing says these two lines intersect infinitely many times. That's what it really means. And now it says, this problem says, if they intersect infinitely many times, then they are identical. They intersect always. And how are you ever going to prove such a fact? So, one thing about polynomials, say p of x is equal to, say, the sum till m. Actually, let me not use the sign, let me use another symbol. So, we have that p of x is going to be, say, a0 plus a1 times x plus all the way till an times x to the n. And say q of x is equal to b0 plus b1x plus all the way till bm x to the n. Right. Let's assume that m is greater than or equal to n. So now, how do you use this condition of equality? Well, you can use this condition, but you don't know what these x's are. But you can use a subtraction. You can subtract this. And what you get is, if you subtract q of x minus p of x, you're going to have, say, b0 minus a0 plus. Now, we're going to have b1x minus a1x. We get x outside. And we have b1 minus a1x plus all the way till bn minus an x to the n plus maybe some bm to x to the n. Maybe. Right? This is if m is greater than or equal to n, which we can assume without loss of generality because everything's symmetric with respect to p and q. Now, this thing right here is also what? It's also a polynomial. And we can in fact call this polynomial r of x. Now, now some of these things are going to be zeros, right? It might actually be, I should just say that an and bm are both not equal to 0. This is how you would usually write this down. A0 can be 0, but it's usually just said these two are not. So with that in mind, this is a new polynomial. And what do we know about this new polynomial r of x? Well, let its coefficients be r of x, let it be equal to c0 plus c1 plus, times x plus all the way till c, let's call it c t x to the t, where t is sum, t is less than or equal to m, right? And c of t is not equal to 0. Then this is another polynomial. And this is the cool thing about polynomial. This isn't true for any old function that you can do this, but for polynomials it is true. If you subtract or add two polynomials, you multiply them, you can get a new polynomial. And then you can use things for that polynomial. And now what do you have? You have r of x really is going, this condition says r of x is 0 for infinitely many x, prove r of x is always 0. And what does it mean that r of x is 0 for infinitely many x? That means there's x1, x2, there's infinitely many values here which are different from one another such that r of xi is going to be 0. Now, what do we know about polynomials? And this is crucial. If r of xi is 0, then r of x can be written as x minus xi times some other polynomial, say t of x. And this is very important because from here we get that r of x can be written as x minus x1 times x minus x2, and all the way till infinity. We can have infinitely many xi's. But then what is the degree of, and of course there's a, at the end you can have a constant term outside, which here would be ct. And that ct is just so when you multiply all the x's together, you get that, you get this coefficient near the highest degree. That's why you have that. And here what this says is that the degree of r of x is infinite. That's what it says, because all of these are different. Because you can imagine, you can factor r of x as x minus x1, and then for t of x, you have t of x2 needs to be 0, because r of x2 is 0, this isn't 0, so you can factor it as x minus x2 again. And so on and so forth. You'll get an infinite number of them. But if you're getting an infinite number of them, then you're getting the degree is going to be unbounded, right? It's not going to be a number at all. So this tells you that if a polynomial has infinitely many zeros, or more zeros than it has a degree, than its supposed degree, then that polynomial is actually a constant polynomial. That means that r of x needs to be 0 for all x. Because it's 0 for infinitely many of them, it's 0 for all of them. And this is a cool little thing. How could you maybe, now you might be asking yourself, how can I actually prove this formally? This doesn't seem very formal. And I would say this. You can say, assume that r of x has a degree that's greater than or equal to 1, right? Then it has, and say that degree is t. By this fact, it has at least t zero. By this fact, it has at least t different zeros. It has infinitely many different zeros, but it has at least t of them. Let those zeros be x1 through xt. Then by this rule, which is I think called Bezout's theorem, we can write r of x as c of t times x minus x1 all the way till x minus xt, by repeatedly applying this rule and getting a polynomial of a lower degree, and then we're done with this. So now this actually finishes up the factorization of r of x, but then you could say, but we also know that there's another 0, xt plus 1, such that r of xt plus 1 is also 0, but it's not equal to any of these. Then we get this side is 0 and this side isn't, which is a contradiction. And so our assumption that that you can actually, that this is a polynomial of degree t greater than or equal to 1 has led us to a contradiction. So r of x is actually of degree 0. R of x is equal to a constant. This is, if it's 0 once, that means that constant is 0. R of x is identically 0, and so p of x and q of x are equal to each other. This is an introductory thing with polynomials. And in the next video, we're going to do a thing for number theory in polynomials. And I'll see you there. And as always, thanks for problem solving.